Welcome to Higher Structure Seminar Series of Feza Gürsey Center for Physics and Mathematics. Today our speaker is Simon Willerton from University of Sheffield, and he will tell us about the projection formula, extranatural transformations, and surface diagrams. And we thank Simon for giving this talk and contributing to our seminar series. Please, Simon.
Great, thank you very much. Oh, I forgot to ask, how long am I supposed to speak for?
It is approximately 1 hour, but the record is 1.5 hours by Urs Schreiber.
Right, yes, 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 that doesn't surprise me. Yes, I will possibly, yeah, well, I'll try to stick to an hour. I'm not exactly sure on the timing, but anyway, okay. So probably on the shorter side is my guess, but we'll see. So thank you very much for the invitation and the opportunity to speak. Wasn't quite sure where to pitch this, and I guess I wrote the title before the talk, and so there's lots of things in the title, and it'll sort of be a kind of a bit of a journey around some of these things, and we'll see where we go. So wasn't quite sure where to pitch, but anyway. So just on the right screen. So, I mean, one thing I want to try and do is think about what closed monoidal categories are, or where they fit into sort of high categorical structures. So that's kind of where we're going to end up using monoidal double categories eventually, but we'll see that right at the end. And we'll see a few things along the way. But firstly, let me just give you just this slide here on monoidal categories, just to give a bit of a context. So if we're thinking about a monoidal category in the context of kind of higher category theory, so we can think of as a monoidal category as being a pseudo-monoid in the monoidal 2 category of categories, functors, and natural transformations, where the monoidal structure is the Cartesian structure. So let me just kind of say that in a bit more detail. So well, what's a monoidal category? A monoidal category, let's just look down here. So we've got a category M, and here this box product, this is going to be the Cartesian product in categories. So we've got a tensor product, which is just a functor, and we've got a unit object for the tensor product, which we can represent as a morphism from the unit object in the 2 category. So that would be just the category with one object into our category, and that's just going to pick out the unit object in our monoidal category, and it satisfies sort of associativity and unitality up to these 2 cells. So that would be the structure of a monoidal category, but I've expressed it here without talking about any elements, any objects of the category M. So I've sort of phrased it in a language where I can then, as I say, I can say I'm not necessarily restricting myself to working in the monoidal 2 category of categories. I can work in any monoidal 2 category. This definition makes sense there, and that's this abstract definition of a pseudo-monoid in a monoidal 2 category, and in particular, a pseudo-monoid in cat is just a monoidal category. Okay, so we can phrase the definition of a monoidal category in this higher categorical sort of framework, and then talk about analogues of monoidal categories in other 2 categories, say monoidal 2 category of enriched categories, or various other things you might want to do it. So the question then is, can we do a similar thing for closed monoidal categories? Okay, so we can do it so what is a closed monoidal category from a higher categorical perspective? So that's sort of one of the themes I'm going to be talking about. Okay, so let's just have a first look at closed monoidal categories. Okay, so a closed monoidal category is a monoidal category with an internal Hom. Okay, so that's going to be a functor. I mean, so typically, you'd write square brackets for the internal Hom. It's kind of convenient in what I'm going to do to write it in this infix notation, this lollipop notation. So think of A holding a lollipop pointing at B. So that's the internal hom from A to B. Okay, so this is a functor. So I've just realized my M has turned into a C here. So C is going to be a monoidal category, but I'm giving this extra structure, this internal hom. So we get a functor from C op cross C into C. And such that for any object in C, we have this adjunction, this sort of hom tensor adjunction. So tensoring with any fixed object in C is left adjoint to homming out of that object. Okay, so they both give us functors from C to C if we fix an object A. Okay. So that's sort of your usual kind of definition of what it's one definition of a closed monoidal category. So we can think about this adjunction here. So in particular, what we have is sort of a unit and co-unit for the adjunction, which turn out to be what are often called sort of evaluation and co-evaluation. So yeah, if we've got A tensor, the hom from A to C, we can do the evaluation of an element of A and a thing in the from A to C, and we end up in C. Okay, and similarly, there's the co-unit for this adjunction. The unit for this adjunction is the co-evaluation map. So for every A and C, we have a morphism of this form, and these are going to satisfy the triangle identities because this is an adjunction. Okay, so for every A, we have the adjunction, and so that gives us one of these for every C. Okay, so typical examples I think of when I'm thinking of closed monoidal categories would be like finite dimensional vector spaces or finite dimensional representations over some finite group G. These both have internal homs. Okay, so we want to have this definition, but in the same sort of form that we had the definition of our monoidal category. So the definition here, we didn't use the internal structure of M at all. So we kind of didn't make reference to any objects in the category M here, which was this formal definition, which allowed us to generalize it to other two categories. So that's what we want to do here. We want to describe this formally without reference to objects in C that we've got here. So, we would like to sort of describe it as a functor with a natural transformation satisfying some properties, or etc. But the problem here, the problem you run into, is that these evaluation and co-evaluations do not form natural transformations. Okay, so the issue here is, if a natural transformation is natural in a variable, then we're going to want to have it on both sides. So it's not going to be natural in A. So this evaluation is natural in C, but it's not natural in A. It has a different property called extranaturality, which we're going to see. But so we're going to have to kind of define what this abstract structure is that these satisfy, okay, in order to go there. So let's then talk about what an extranatural transformation is. So I think these were I realized I've not written down any references in this talk at all. There was a preprint mentioned in my abstract, so I've lots of references in there. If I forget to mention people, it is mentioned in there, so I do apologize. But extranatural transformations, I think it was Allenberg and Kelly who first came up with the notion of extranatural transformations. So we have we're going to see a lot more abstract definition of this much later on, but for now, just take this kind of very concrete thing. So the idea is that we've got two functors and they have a certain sort of form. So we've got a functor f, which goes from a category across its opposite, across another category into some domain. Oh, sorry, there's a typo there. That should definitely be a C. And I don't think I can write on here, can I? Yeah. So let me just see if this works. Oops. So, whoops, I didn't want to strike through that. But this B, sorry, should definitely be a C. As you can see here, that's a C. And the other functor has, so we're going to have the C appearing in the G as well, but we have two other categories, B and its opposite, but we have the same codomain D in both cases. So we're going to have an extranatural transformation going from F to G is going to consist of the following data. So for every A, B, and C, obviously A in A, B in B, C in C, we have a morphism in D of the following form. So it goes from F of AAC to G of CBB. So both of those variables take in the same thing when we look at this morphism here. Okay, and it's going to satisfy some properties. So it's going to satisfy extranaturality in A and extranaturality in B and naturality in C. So I've just given the extranaturality in A here. So if we have any morphism F from A to A prime in A, we get that this square here commutes. So if we apply, so this is contravariant in the second variable. So if I apply F to the second variable, it's going to go from F of A primed in the second variable to F of A in the second variable. We do that, and then we apply this component map here, EABC. It's the same as applying F to the first variable, and then which gets us to F of A primed C, and then so now we have both of these being A primed rather than both of them being A's like it is there. We can go to we can apply E A primed BC. So this is the extranaturality square. So we get the naturality between things on the same side. So an extranatural transformation is going to be this plus naturality in C plus a similar diagram, but you can kind of figure it out. But where we have here extranaturality in B instead. Okay. So that's the definition of an extranatural transformation, and so it turns out these are you do know of these, some examples of these, whether you are aware of this or not. So an example would be if we take our functor f. So we're going to take A to B category vector spaces. So that's the vector spaces opposite. B we're going to take to be the trivial one object category, so that just disappears when we cross with it, and the D we take to be vect, and our G we just take both C, that was supposed to be a C, sorry. C is the trivial category, but we also want B to be the trivial category. So this is just the trivial category mapping into vect, and I'm just taking the constant functor, which picks out the complex numbers, okay? So, evaluation, we took the functor, which takes a vector space tensored with the dual of the second vector space. Okay, so if we've got a V and W, we just take V tensor W dual. Okay, that's a functor from vect cross vect op into vect. And so there is a natural transformation, extranatural transformation between these functors, which is the evaluation. So our component of this just takes element of W and an element of a dual and evaluates it on. And this satisfies this extranaturality. So if we have any f from v to w, so inside vect, evaluation satisfies this property. Evaluate, we take f of some element in v and then evaluate some dual of w on it. That's the same as applying the dual of f from w dual to v dual first, and doing the evaluation there. So this is a sort of, whether you're familiar with this or not, you have done it even if you've not seen it precisely in this form in the undergraduate things where you're kind of doing the dual of a linear function. So this is a sort of concept you'll have intrinsically know about somehow, but now we can define a closed monoidal category using this concept of extranatural transformations. Okay, so we can define a closed monoidal category to be a monoidal category. Oh, and we've gone back to M again. M tensor together with an internal Hom functor, which I'll write as lollipop, together with extranatural transformations, evaluation and co-evaluation, which have the following form, and this barred double arrow, I mean extranatural transformation. We have evaluation and co-evaluation satisfying triangle identities. Now let me just look at this form of this. So evaluation and let me just go back to a slide here. So what we do with evaluation, we do the internal Hom first. So we've got three variables. We leave the first variable as it is, do the internal Hom of the second two, and then we tensor the two results together. So that's the evaluation, and we just map to leave the last variable as it is. And so that's the form we've got here. So we left the first A as it was, and we crossed with the internal Hom. So we did the internal Hom of the second two variables, and then we tensored the result together, and we were going into just the identity thing on the last variable. We'll keep track of the variables a bit better later on when we get to the graphical calculus. And similarly, the co-evaluation had that form. So co-evaluation goes from just do nothing to the final variable, which is just the one which we're natural in. But otherwise, we do leave the first variable as it is, tensor the second two together, and then do the internal Hom for the result. So that gives us this shape here. Leave the first thing as it is and tensor, and then do the internal Hom. So that's the kind of right shape of those. But we'll see that a bit more later on. And these satisfy triangle identities, and I'm not going to write them down at this point, but we'll see them kind of graphically a bit later. Okay, so I'm sort of saying we're going to see this graphically. So the idea is that what we're going to see is that this sort of fits nicely into a graphical framework of surface diagrams, and then we're going to see how that's fitting into a monoidal double category. So before getting there, let's just do, before getting into monoidal world at all, let's get into string diagrams for the two categories of categories. Well, the string diagrams will work for any two category, any bicategory. But if we have your usual globular notation for natural transformations or two cells, so we've got categories B, C, and D. We've got a functor K from B to C and from C to H, and a natural transformation between the composite and J. We can write this down in terms of string diagrams. So we take the dual of this picture. So now here in this globular notation, we have alpha. So this two cell is a region. We represent it as a point, as a zero-dimensional thing in the string diagrams. And each of these functors we now represent by the sort of dual. So we're taking like the Poincare dual of this picture to get this string diagram here. So now B, the category B is represented by this region, and we transition. So the functor J, we go from B into D. So the functor K, we go from B into C, and H, we go from C into D, etc. And alpha is taking us from K followed by H into J. And here I'm just recording that I'm doing my which way my orientation is. So I'm going from the which side is that? From the right there I should say that is probably that side if I'm mirrored, into the other side. I'm going from bottom to top. So that's my convention for sides. Okay. So any sort of natural transformation I can represent in this string diagram way. And so the classic example of where this is nice is for an adjunction. And I realized I think I'm going to call my adjunction. So here I've called it F and G. I think I might switch to F and U in a minute. But if we have a left adjoint F and a right adjoint G, then we have a co-unit for the adjunction and we have the unit for the adjunction. And we represent that as, so let's just have a look at the co-unit here, going from left adjoint composed with the right adjoint into the identity. So this would be pictured like this. So F composed with G into the identity on D. And we have the epsilon is this natural transformation here. So that's how I would represent that in string diagrams. You can translate it into Grobdier pictures if you like. But in string diagrams, we will just often omit identity functors. I mean, you can get away with omitting the identity functors. They're just sort of assumed. You can add them or remove them. It doesn't matter in the notation. And we'll often, in an adjunction, we won't actually write the red dot. We'll just use the top of that little cap there, and it's sort of understood that's what we have. So we'll write this co-unit in this fashion. So we've got something going from do G and then do F into the identity on D. Okay, and similarly for the unit, it goes from the identity on C here at the bottom into G composed with F. So this represents that natural transformation. So then the triangle identities, if you write down what these are, you sort of do the identity on F, then you do the unit, and then you do the co-unit, and that turns out to be equal to just the identity on a natural transformation on F. So that's what that straight line represents. So this is a natural transformation, and it's just the identity natural transformation on F. So you have this very nice pictorial representation here of adjunctions in terms of string diagrams, and you get this sort of the topology here is really reflecting the category theory. Okay, and similarly the other triangle identity is we can just straighten out that little loop there. Okay, so that's a quick run into string diagrams, because we're going to get more complicated. We're going to talk about surface diagrams now. So string diagrams will work for any bicategory. I mean, I was talking specifically about the two categories, functors, and natural transformations here, but we're going to use the monoidal structure, and so we're going to use another dimension. So what we had there was, if we had functors, we represent composition of those right to left. We had composition of natural transformations. We were going from bottom to top. Now what I want to do is I want to be able to tensor things together. I mean, use the product of categories. So that's another composition, and I'm going to do that into the screen. I don't know, is that coming out or going in? It's one or the other. So I think of that as going into the screen. So here I've got category C and D. So if I draw C and D like that, that means C crossed with D. Okay, so I represent it like that. So here, and again, this is sort of supposed to be flat, but going into the screen. This is representing a functor, so because it's just on the flat level, and the domain here is C cross C, and we're going in this direction into C. Okay, so this represents a functor from C cross C into C. So if we have monoidal categories C and D, so in particular, yeah, I mean, we can represent that. If we have a monoidal category, we can represent the tensor product in this way, because that's the form of the tensor product. So if we have monoidal categories C and D and a functor F from C to D, Suppose we have a natural transformation with components of the following form. So for instance, if f is a monoidal functor, then a lax monoidal functor, we're going to have a natural transformation with components of the following form. So for every c and c primed in c, we've got something from fc tensor fc primed into f of c tensor c prime. Then the form of this natural transformation, well, it's what are we doing here? So we're applying f cross f first to c cross c, and then we're doing the tensor in D, and on this side we're tensoring together first, and then we're applying f. So we can, so we just write that in sort of component-free component-free notation. It's a natural transformation from the composite of the tensor with f cross f into f cross tensor. So we can represent this in this sort of string diagrammatic way, this surface diagrammatic way. So so if we look at this, excuse me. So if we look at this this natural transformation, so the domain is do f cross f first, so we're starting at c cross c, and then do the tensor. So if we look at this picture, so we're supposed to read this, we start at the bottom with c, so at c cross c we apply f to both copies of c, and then we apply the tensor in D, and that's the that's the domain there, and the codomain is the functor going from c cross c, where we apply the tensor first and then we apply f. Okay, so this picture here represents a natural transformation of this shape, and we just represent it as the strings just crossing through through this sort of edge formed by the tensor product there. So that's how we would represent something like the structural natural transformation for a lax monoidal functor, okay, in that form. Okay, right. So let's just say so this will work then for any monoidal 2 category. So I can think about this as representing natural transformations in the monoidal 2 category of categories, functors, and natural transformations, but it will equally, we can use this to represent 2 cells in any monoidal bicategory or 2 category. But what I want to do is I want to represent extranatural transformations, which is slightly different. And it turns out these work very well in terms of this notation. So, but extranatural transformations, we have something, we had a few things that we don't find in sort of common or garden monoidal 2 categories. So we had the opposite structure. So given any category, we can take its opposite. So that's a sort of a transformation on the 2 category of categories, but it's special to the 2 category of categories. It's not something you find in every 2 category. But let's just think about taking opposites. What does it do? So if we have functors G, H, and K, and a natural transformation between the composites, and we look at what happens when we've got opposites. So if we've got a category B and a category D and a functor K between them, when we get a functor between the opposite categories. So we get a corresponding functor from B op to D op. Okay? So that doesn't switch around. I mean, we still take objects and it behaves in the right way for a functor between them. But what happens if we have a natural transformation? Well, it switches a natural transformation around, because the opposite, we reverse the morphisms inside the category, and the natural transformation components are defined in terms of the morphisms in the category. So if we switch around the order of the morphisms in the category, then the components of the natural transformation will switch around. So what we get is that a natural transformation from H composed with G to K gives us a natural transformation from K op to H op, G op. I mean, it's the same, it's the same thing, but because we just keeping track of the opposites. I mean, it's essentially the same natural transformation, but we're thinking of it as going between the other things. But the direction of that is switched. So functors keep the same direction, but natural transformations will switch around when we do opposites. So in terms of the surface diagram notation, I'm just going to write this. I'm going to drop the ops, but I'm going to color in my sheet when I'm talking about opposites. And it's, so I'm going to think of this as being like the reverse side of the piece of paper. So my piece of paper is white on one side and blue on the other. And so if I take this one here and I turn it upside down, I will see the back of the sheet, which is what we have here. So, and this makes this, as you see, is going to make sense. So suppose we've got two functors, the right sort of shape for taking a natural transformation, extra natural transformation between them. And we've got this extra natural transformation beta going from P to Q. Then I'm going to represent this by this diagram here. So now, note again, we'll just check the domain and the codomain. So at the bottom, we're going from P, which is a functor from C across C op, and it's C op because it's in blue, and then A, and we're going to D over here. So that's P. So that's the right structure. And again, up here, we're going from A across B op across B. We've got Q going into D. And so beta is going to be the natural transformation between them. And I can represent it like this. So C doesn't appear at the top, but what happens is it sort of curls in on itself. So I'm going to represent such an extranatural transformation in this fashion. Okay. And I've just highlighted here what's going, if we just look at the edge of this thing here, this face here, this is telling us which elements, which of the parameters or variables in the functor have the extranaturality and which have the naturality. So it's natural in A because that's appearing both sides, and this is just keeping track of what's happening in these. Okay, yeah. So that this face here is recording the information about where the extranaturality is going on. Okay. Now, I'll just go back to our surface diagram. So, I mean, I didn't make the point here, but we can compose these in the sort of in all three directions. So if we have such surface diagrams, we can compose them on top in the extranatural transformation, in the natural transformation direction. We can tensor them together into the page, or we can compose them in the functor direction. Okay, and we can compose here as well with natural transformations. So we can compose this on the left there with another natural transformation going from, we can compose P with some functor K and compose Q with some functor K primed and compose beta with a natural transformation between K and K primed. Okay, and similarly we can do stuff at the other side as well. If we have something from, if we have a functor, natural transformation from H prime to H, which would be our theta here, we can compose that on this side. And I'm not going into details, but the extranaturality is saying that we can sort of move these natural transformations up and under the curve here. Okay, so that's what kind of you translate what this sort of thing here was doing, like the evaluation. We can apply it on the one side, or we can apply it on the other before doing the extranatural transformation. And when you sort of figure out what's happening with these diagrams, that's beautifully encoded in that we can just move these beads around in this way that you would sort of expect. And that's the sort of nice thing about having the sort of the backside in blue of these things. Okay. So now we can define our closed monoidal category diagrammatically. Okay, so a closed monoidal category in this language then, so we've got a monoidal category C tensor, so we're going to have our tensor functor, and we're going to have our internal Hom functor, and what we wanted, let's just nip back to the definition we had. So we've got, and my M has become a C, I do apologize. We've got these extranatural transformations of this shape, one going from tensor composed with id cross the internal Hom into id, and co-ev with a similar thing. So in our graphical notation, we have ev going with so again, we're reading that way. So we've got the C op C, and we do the internal Hom on the last two and the id on the first one, and then we tensor the two results together. So that's our domain of the extranatural transformation, and it's just the identity on the top. So we just draw the evaluation extranatural transformation in this way, and the co-evaluation in this way. It has that form. And then the triangle identities have this sort of simple form, which you can see is very similar to the triangle identities we had there, where we're just pulling strands out. So the triangle identities they're required to satisfy are just this. You can just write them in this form, where we're doing a composition of co-evaluation and evaluation extranatural transformation, and we can just pull it straight to an identity natural transformation. Okay, so this is our nice compact definition of a closed monoidal category without any sort of reference to the objects of C here in this graphical language. Okay, so this relationship here between tensor and the internal Hom, I mean, this generalizes to a notion of an adjunction of two variables. So it's related to the idea of a parameterized adjunction, which is sometimes a way of expressing the relation between the tensor and internal Hom. But I call it adjunction of two variables because it's slightly different setting here. But so if we have a functor T, which stands, I've called it T for tensor, of this form A cross B into C, and we have H, which I think of as being the analog of Hom, we've just opt A and we switch the role of C and B round. So if we have two functors of that shape, we're gonna say that T is the left adjoint of H. If we have a unit, which is the co-evaluation, the equivalent of that, where I just replace the tensor with a T and an H there, and a co-unit, which is going to be the analog or the equivalent of the evaluation there, and satisfying these triangle identities. Okay, so we can just replace tensor and internal Hom with slightly more general forms of functors, but these two bits of data are essentially the same. So that's an adjunction of two variables. Note that if you replace A with a trivial category, the one object category, the terminal category, that just reduces to the usual notion of an adjunction. Okay. So I just write T with two bars H. So for example, we have tensor is a adjunction of a left adjoint of two variables with the Hom. Okay, so let's go back to ordinary adjunctions now, and we've got the notion of conjugation. So given if we've got two adjunctions sort of the same shape going between the same categories C and D, we get the notion of conjugation. So we've got these two adjunctions. Now if we have a natural transformation from F to F prime between the left adjoints, that's we've got a one-to-one correspondence between natural transformations between F and F primed and natural transformations between U primed and U. So we've switched the order there, the U and U primed, and we can just draw this correspondence quite easily diagrammatically. So if we've got this natural transformation from F to F prime between the left adjoints, then we can just compose this with the sorry, I've forgotten whether I'm using the word evaluation or co-unit here. So this is the co-unit for the primed adjunction, and I use the unit for the unprimed adjunction, and so then that gives me automatically gives me a natural transformation from U to U primed. And this is a one-to-one correspondence. So if I just going the other way, I would just stick the unit on that side and the co-unit on that side, jiggle them about in a way I'm going to show, and then use the triangle identity. That gets you back to theta. So you get this one-to-one correspondence, which is nicely expressed in terms of these string diagrams. So this preserves composition, well, up to change of order. So if we say, call this the conjugate, this natural transformation here, the conjugate of theta. So we take the conjugate of theta and do it after the conjugate of theta primed. Now I can just move these diagrams around. I just move this theta primed up here, this theta primed down here, and I get this picture. And then I can just cancel out using the triangle identities. I can just cancel out the hump here, and I just get the conjugate of theta followed by theta primed. Okay, so this preserves composition up to change of order, which is what we'd expect because we're reversing on this side. So conjugation gives us this one-to-one correspondence. I mean, there's actually a sort of a equivalence of categories going on there, but I won't go into that. But because it preserves composition, that means that theta is going to be invertible. So this has an inverse if and only if its conjugate has an inverse. So a natural transformation is invertible if and only if its conjugate is invertible. So this is a nice property that conjugates have. Okay, so we can do the similar thing, the analogous thing for adjunctions of two variables. So if we have two adjunctions of two variables, we've got a t and an h, and a t primed and an h primed, and these are both going between the same triple of categories here. So A cross B to C and A op cross C to B. Then we get the same sort of relation. So the natural transformations between T and T primed are in one-to-one equivalent, one-to-one correspondence with natural transformations between H primed and H. So again, we reverse the order and we get the same sort of picture going on here. So if we say theta now, natural transformation between T and T prime. So this front sheet here is represents the category A, the back sheet here represents the category B, and the sheet here represents the category C. So we can take its conjugate again just by using the co-unit for the primed adjunction and the unit for the unprimed adjunction. Okay, and to get back, we just put the opposite ones on the other unit and co-unit on. Okay. So we get this nice notion of conjugation, which works equally well in this two variable situation. And again, you know, it will preserve exactly the same proof will tell you that this will preserve composition of natural transformations up to reversing them, because we're going the other direction here. But we get that a natural transformation is invertible if and only if its conjugate is invertible. So we get this nice sort of structure here. Okay, so now let's come to the projection formula. So a lot of this work here, I mean, I guess was me trying to understand a paper of Fauske and May from was it 20 years ago, I think, where they talk about projection formula in various ways. And this was me formalizing a lot of the structures that they do and absorbing it into this surface diagram picture. So just say a little bit about the projection formula. So suppose now we've got a strong monoidal functor between monoidal categories. So I'm going to call my monoidal categories Y and X now. And suppose we've got a strong monoidal functor and it's got a left adjoint. So this crops up in many situations. For instance, in representation theory, in algebraic geometry, these things are reasonably common. So we've got a strong monoidal functor between monoidal categories and it's got a left adjoint. So from this, we can build up a natural transformation that has the following components. So the components have the following form. So I'll say apply f upper star to y, tensor it with x, and apply the left adjoint. We get a natural map to y tensored the left adjoint of x. So let's just think about the structure of this. So we're applying f star to y and nothing to x. So we're doing f star across the identity. Then we're applying the tensor to the result. And then we're applying f pling. So this is a natural transformation from this functor. And here we're doing nothing to y. We're applying f lower pling to x. So we're doing id cross f pling, and then we're tensoring them together. Okay, so this corresponds to a natural transformation of the following form. So f star across the id, and then we apply tensor, and then we apply f star. So that's the domain. The codomain, we just do f pling with the identity on the front one. Then we do the tensor. So that's the domain. Now there's a natural way to do this. So we've got this is a strong monoidal category. So remember I said way back that if the sort of structure map for a monoidal functor looks something like this, and that's exactly what this omega is here. We've got the structure map for the monoidal structure, and we just use the adjunction between f upper star and f lower pling to put that cap and that cup on. So given this data, we get this natural, this canonical, I should say, natural transformation from that data. Now, if this natural transformation is invertible, then it's said that the projection formula holds. And so this holds in nice cases. Now, I'm going to show you how this just relates to the idea of these conjugates here. Now, maybe, I mean, it might help if I zoom in. Can I zoom in a bit here? I'll have to move out the way. So if we take, it turns out, so I can take the conjugate of this natural transformation here. So in the same sort of way I've done here, I've got a natural transformation. It turns out both the domain and codomain have right adjoints in this two variable sense, and so we do that by just putting omega into we just put pi, this picture here, which is sitting down here, inside appropriate unit and co-unit. Now we can wiggle this about a little bit. So let's see if I can. I've just put this pi in here, as I say, and done a unit and co-unit, and I can clearly pull this string straight, use the triangle identity, and pull that string straight until I get this thing here. So that's equal to that natural transformation. And so what we get is, if you now read what this diagram is doing, this is going from at the bottom, we do the internal hom and then we do f upper star, and we're going to do f upper star on both the bits at the top, and then we do the internal hom. Okay, and if we work out what the components are, it looks like this form. Okay, so we get there's a sort of a natural, canonical natural transformation in this situation from the f upper star of the internal hom to the internal hom of after we've applied f upper star. Now, if sigma is invertible, we say that the f upper star is strong closed monoidal because it's preserving, f upper star is preserving this internal hom. But we know from what we've said that a natural transformation is invertible if and only if its conjugate is invertible. So we get that the projection formula holds So this is invertible, pi is invertible means the projection formula holds this is an isomorphism, if and only if this is an isomorphism. So, I mean, this is a sort of, it's been kind of known for a long time that, projection formula holds if we have a strong closed monoidal functor, but this is putting it in the context of really seeing what, these are just conjugate in a formal sense of these two variable adjunctions. So it's putting it into that context, this sort of this result, which a well-used result. These are just conjugate. Right, yeah. So this was the sort of projection formula part of the talk. So this is seeing how these extranatural transformations, how this diagrammatic calculus gives you this a framework for understanding this result. Okay, so I've got another 10 minutes left. So I think I've got 3 slides left. So I want to talk about where this is now sitting in higher category theory. So maybe if we just go back, I mean, so the monoidal category, I said, I can define that in the analog of that, the pseudo-monoid, the definition of that makes sense in any monoidal 2 category. We can abstract the monoidal 2 category of categories, functors, and natural transformations, and we've got the definition of a pseudo-monoid. However, the definition of our closed monoidal category uses extranatural transformations. Extranatural transformations are not part of the data of a monoidal 2 category. This is something special about the 2 category of categories. This is extra data that we've got. So for instance, we needed to use the opposites of categories, for instance, but this is an extra thing, the notion of what an extranatural transformation is. Okay, so I just want to think about what the higher categorical context for that is. This involves double categories. Okay, so double categories are another 2-dimensional categorical structure, and here we've got 2 kinds of arrows, and we're going to use string diagrams again. So I'm going to call my my 2 kinds of arrows loose arrows and tight arrows, rather than vertical and horizontal, because people use different conventions for vertical and horizontal. So I'm going to draw my tight arrows horizontally and my loose arrows vertically, and I'm going to have a 2 cell. So the idea is that a double category has these tight arrows that I can compose tight arrows together, and I can compose loose arrows together, but I can't compose loose arrows and tight arrows in general. And then I've got a notion of what a 2 cell is. Before doing the string diagrams, maybe let's just remind you an example. So I can take bimod, where my objects are algebras, let them for concrete sake, let's say algebras over the complex numbers, and my tight arrows are just going to be algebra maps. Okay, so just your usual morphisms in the category of algebras. Excuse me, but my loose arrows are going to be bimodule. So a loose arrow, which I denote with a bar on it. So, well, let's go over this side. M is going to be an AB bimodule. So A is acting on the left, B is acting on the right. Okay. And so I can compose bimodules. If I've got an AB bimodule and a BC bimodule, I can compose them by tensouring over B. So that's how I do my loose composition. And then I have a 2 cell. So here I've got 2 algebra maps and 2 bimodules. What is a 2 cell? Well, a 2 cell is going to be, the idea is I've got, sorry, that should be M primed there, not N. The idea is that I can use G and G prime to pull back M primed to an AB bimodule, and then a 2 cell is just a bimodule map from M to the pulled back bimodule. Okay. So this gives us a double category of bimodules. Whoops, don't want my, whoops, go away. Right. And we similarly, so sort of we can sort of expand that or generalize that. So we have a double category of profunctors. So the objects here are categories, the tight arrows are functors, and the loose arrows are profunctors. So a loose arrow from A to B means a profunctor, which is just an ordinary functor from A up cross B into the category of sets. Okay. And so if you think about what a bimodule is, you can sort of phrase bimodule. If you think of an algebra as a one object category, then a bimodule is sort of is a functor into vect, so A up cross B into vect. So this is very similar to that notion there. But the two cells, we do the same sort of thing. So a two cell, if we've got a functors here and profunctors there, so it's just going to be a natural transformation with components of this sort of form. So we form a profunctor from AB by essentially pulling back this profunctor from C to D along these functors. Okay, and it's a natural transformation. A two-cell gamma is a natural transformation between them. Okay, and we can use a string diagram notation in the same sort of way. So before I just had these vertical bits, but I can add on strings taking into account. So I had nothing on the sides before. So here I'm just adding decorations to the sides, and these come into the two cell. Okay. Now let's give you two examples of a few examples of some special profunctors. So in particular, if we've got a category C, we've got the Hom profunctor, which I just write as C blank blank. So the Hom profunctor, the Hom functor, just spits out the set of morphisms. If we put C and C primed in, just spits out the set of morphisms from C to C primed. So that gives us I can think of that in many ways in terms of profunctors. I can think of that. So remember, the structure of a profunctor, a profunctor from A to B means A up cross B into set. Okay, so the Hom functor is from C up cross C into set. So I can think of that as a profunctor from C to C. Turns out that's the identity profunctor. I haven't told you what the composition of profunctors is, but it generalizes the composition of bimodules. So we get the identity profunctor from that. But I could also, cross this with the trivial, the one object category, which is the identity object for the Cartesian product, and make no difference. So I can then think of that as something from C op cross C opt into the one object category. Okay, so I can just switch my perspective and think of that as the domain and the star as the codomain. So I can think of it as a profunctor from C cross C op into star. And similarly, I can put the star on the other side, and I can think of this as being the domain, the codomain, and star as being the codomain. So I can build three different profunctors all from the same Hom functor. And these, it turns out these, if you might recognize these as being like evaluation and co-evaluation for dual. So it turns out, and I won't go into details, this makes C op into the dual of C in the bicategory of profunctors. So we get this sort of structure there. So it turns out that if we think of prof, just not the double category, but it as a bicategory, then this is monoidal and it has duals, and the dual is just the opposite of a category. Okay, so final slide then, putting these things together. Oh, sorry. So I did mention the string diagram. So now it turns out that an extranatural transformation can be phrased in a different way. So if we've got a functor from C cross C op cross A into D and another one A cross B op cross B into D, then an extranatural transformation between them is actually essentially the same thing as a natural transformation with components of this form. Now let's just go back to what a extranatural transformation was. So here F and G have become P and Q. I do apologize. So these are my P and Q. So what I have when I plug in the same variable in the first two components, two entries there, and the last two components there, I get a map between them. So what I am supposed to have here is a morphism in D from P of C primed A, Q of A primed B, B primed. But if I make C and C primed the same, I can say, well, inside here I've got the identity function from C to C. Here I've got the identity function from A to A. Here I've got the identity function from B to B, as long as I'm making B and B prime the same. So I can look at the image of that when I put the identity maps in those, and that's going to give me a map in D from PCCA into QABB. So that's going to give me the data I had of an extranatural transformation. And it turns out the extranaturality is then encoded in what happens, the naturality of this. So this is another way of saying what an extranatural transformation between P and Q is, okay, as the natural transformation of this form. But, this is the same as the data of a two cell in this monoidal, in this double category of profunctors. So if we just look back here, so a two cell gamma was going from components going from the thing on the left here into the pullback thing on the right. So going from the thing on the left here, well, I'll just say what that is in a second, into the pullback thing on the right. So I'm using P and Q to pull back the identity profunctor, but the identity profunctor is just D. That's what I was saying here. So the identity profunctor is just the Hom functor, and I'm just thinking of these Hom functors here in terms of, I'm just rewriting them as these sort of profunctors with this different variance on them. So putting them all together, this extranatural transformation is the same as a two cell of this form. So if I write that in string diagrams, I've got the identity here, so I can ignore that, and that string diagram becomes of this form. Now, what I want to do is just use the third dimension, as I've done previously, just to go into the plane of the paper here and just use this monoidal structure. So if we see what we've got at the top here, we've got A cross B op cross B. So we've got A, B op B, and C op A. And EC was just going from C cross C op to a trivial thing. So I'm just representing this as this closed map here. Okay. So the idea is that if I think about string diagrams and this double category of profunctors, functors, and natural transformations, then I naturally get back my my surface diagrams for extranatural transformations. So although I just sort of started with this as an ad hoc way of representing an extranatural transformation, in fact, it has this really natural interpretation as being something in this monoidal double category. So monoidal because we're going into the depth there, into this monoidal double category of functors, profunctors, and natural and these two cells. So that's where these extranatural transformations are really living. So they come down into the into the two category of categories as this sort of shadow of things coming from the two category with duals of profunctors. So this is really the context in which we define closed monoidal categories. So this is the context in which we can define extranatural transformations, and this is the higher categorical context for defining closed monoidal categories. So we've got categories sitting inside this double category of profunctors. So when we're using this structure of duals for profunctors there. Okay, so I sort of sped up quite a bit at the end as we got to this abstract structure, but that's sort of the kind of overall sort of picture I wanted to give. So I will stop there.
Thank you very much. Any questions or comments?
I have a question.
Hi.
Hi, I have a general question. If we do not consider objects of a category, is it easier to work with one object categories?
Right. Do you have something in mind there? I mean, I guess so. Yeah. So are you saying how would you categorize something with one object? I don't.
I mean, there are categories with one object,
Yeah.
and um, um, and considering only functors and natural transformations, neglecting objects in a category.
Yeah.
Can this make the understanding easier of one object categories?
Yeah, I mean, I've not really. I mean, I think a lot of it. I mean, so I mean, this example here with bimod is. Whoops, sorry, that wasn't supposed to happen. Will that go back? So I've lost my. Right. Yeah. So this situation here. So that's just the one object case. Well, I mean, enriched one object case of this situation here. So so you can certainly talk about the one object things in exactly the same language. I mean, whether it makes it easier or not, I mean, I guess that's a question of taste somehow. But one can certainly. I mean, I would definitely think about these one object case in the same way. Yeah, and whether it makes it easier, I don't know. Yes, yeah, but I mean, if you have a specific thing, I can certainly think about whether it's easier or not. Yeah, but certainly the one object things are something very much at the sort of forefront of my mind. Yeah, thank you.
Okay, thank you very much.
I guess there's a question in the chat.
Right. Okay. So how does this monoidal structure fit into the category? Oops. Go away. Right. So how does this monoidal structure fit into the category of sesquicategories? I like to ask in terms of surface diagrams. The main question is, instead of using a bicategory structure like the one you're using in your presentation, could you use the concept of sesquicategory? So I think I might have been in a talk where sesquicategories have been defined, but I can't remember what a so sesqui, I guess, is a 1.5 category in some sense. Vertical and horizontal compositions are with compatible sorts and do not have an interchange law. So I think so the short answer to your question is I've not thought about this. Yeah. Are there obvious examples of sesquicategories? Yeah. Yeah, I don't know is the simple answer. I mean, I'm trying to think if I'm who I've seen speak about sesqui categories before and whether they might be in Sheffield this week actually. Um, but yes, I don't know. I should say actually, while we've just paused, I don't know if as Ross Street is an occasional sort of visitors to this seminar, I should say, yeah, Ross has sort of similar approaches to sort of diagrammatic pictures. I mean, he doesn't work in the double category, just works in the bi category. And in my preprint, I do explain the connections with Ross's work.
Yeah. Thank you very much.
We have a
Uh,
raised hand.
Hi, yeah, thank you. Great talk, by the way. Really liked
Right,
it.
thanks.
So I get the impression from your talk that you want to try and define closed monoidal categories internal to this kind of thing where you need extra natural transformations,
Yeah,
and you're saying that this lives naturally in this double category of profunctors.
yeah,
But at the start, you wanted to move away from defining, so you want to define like a monoidal thing inside a general monoidal category rather than the monoidal category of categories. So
yep,
the
yep,
profunctors is still like this category of categories thing.
yep.
So you need the structure of monoidal stuff, but also it seems some sort of compactness, like
Yes,
dual.
exactly, exactly. So, do you, sorry, do you want to say more, or do you want me to say something at this point? Sorry, I don't know.
All I was going to say after was, have you considered like a more general uh, compact double category thing you could
Yeah.
have this
So,
thing live?
so, so what it's looking like is that, yeah, so we've got a monoidal double category. Well, in fact, a monoidal equipment is the equipment kind of, so the relation between functors and there's a relationship between the loose and the tight arrows. We have conjoints and companions, but that the loose bicategory is compact, as you say. Yeah. So if we work in the situation where we've got sort of we're in a category which is part of the tight part of a double category where the loose part is compact closed, then we can define these structures.
Okay, that's amazing. Thank you very much.
Yeah. So what I should add though is that no one has actually formally defined what that structure is. Yeah. I mean, what is a monoidal double category with half of it being having dual? So yeah. So that definition has not been written down, but yeah,
I
that's what we're
see.
thinking. Yeah.
And so you always say that you have companions and conjoints as well.
Um, uh, so actually, I'm just trying to think whether that. I mean, so relating the stuff to Ross's, that we definitely need companions and conjoints. Whether you need them here, it doesn't actually look like you do. But yeah,
Mhm.
that's something worth thinking about. Yeah,
Okay, great. Thank you very much.
thanks.
any more questions or comments? Uh, Let me check. Yeah. Uh, I think we uh, have no more questions to Simon, I believe. And let's thank Simon once more. And we will meet 2 weeks later again. And the talk will be most probably around the topic of homological mirror symmetry this time. So see you all later within 2 weeks' time. Yeah, bye-bye.
Great. Thank you very much.
Oh, Simon, thanks a lot.
Yeah,
Yeah,
lovely. Thanks.
yeah.
Bye.
Bye.
So, oh yeah, and do tell Ross I said hi as well back.
Oh,
Yeah.
sure. Yeah. Okay, I stop
Yep.
recording.
Thanks.